Good morning students. In the last class we had seen parallel combination of cells. Now we shall come to the series combination of cells. So today's teaching points are written here. We shall find out expressions for equivalent EMF and equivalent internal resistance of two cells in series. Second point, we shall define the terms which are related to Kirchhoff's law. Some important terms related to Kirchhoff's law are network, adjunction and loop. So we shall come to the definitions of this. If you know the definitions of these, then you can very easily understand Kirchhoff's laws. Two laws are there, one is current law, another is voltage law. For all those two laws, we need to define these three terms. So now let us come to the first derivation. We shall find out the equivalent EMF and internal resistance of two cells in series. As we have done for resistors in series, here we have now connected two cells in series. Which are the two cells? Two cells are having EMFs E1 and E2. Their internal resistances are R1 and R2 respectively. They are connected in series between the points A and C. So what do you mean by series connection? Here, the negative terminal of the first cell is connected to the positive terminal of the second. So they are connected end to end between the points A and C. Such a connection, we call it as a series connection. Now this is an equivalent diagram for that. So first we shall write down for the terminal reading across first cell and the second cell. Now what do you observe for this series combination? What remains the same and what changes? As we had done for resistors in series, you can find out when they are connected in series, say I is the current coming out of the first cell, it goes to the external circuit and again I enters the circuit. So what is remaining same in this? So here in the series combination, current passing through each cell remains the same. As we had done for resistor, same thing here. And what is changing? PD across each cell is going to change. E1 is connected between the points A and B. E2 is connected between the points B and C. We shall find out PD across the first cell and then we shall write down PD across the second cell. So here, terminal PD across the cell goes on changing. So based on this, we shall write down the first terminal PD. So I have written it here. For that again the basic relation we use. V is equals to E minus IR. So this relation already I have explained. V stands for terminal PD across the cell. E stands for EMF. I is the current. Small r is the internal resistance of the cell. Same equation we had also used for the parallel combination. Same equation now we shall use to find out terminal PDs across the two cells. Now let us write down the terminal PD across the first cell. You can see the first cell. First cell is connected between the points A and B. So PD across the first cell it is between the points A and B. So I have written the PD across the first cell as VAB. Meaning it is potential difference between the points A and B. So VAB is equals to, put the values for the first cell. E will be replaced by E1 minus R. R will be replaced by R. I is the same for both the cells. I will change. So this is for the first cell. Same thing we shall now do it for the second cell. We shall write down for the second cell. You can see the second cell. Second cell is connected between the points B and C. So PD across the second cell will be nothing but VBC. So that I have written it here. CD across the second cell, it is VBC, meaning this potential difference between the points B and C. So again make the changes in here. Here E will be replaced by E2 minus I remains the same. R will be replaced by R2. So I got PD across the first cell, PD across the second cell. Both are connected between the points A and C. So series combination is between the points A and C. Now I shall find out the total PD across the series combination. It will be nothing but PD between the points A and C. So that I have written here. PD across the series combination. It is between the points A and C. So I have written it as VAC. Now what relation is there between VAC, VAB and VBC? You can see the figure clearly. This is VAC between the points A and B. So this is VAC. So this will be nothing but VAB plus VBC. So as we have done for resistors, V is equals to V1 plus V2. Only here the names are changed. So VAC is nothing but sum of VAB and VBC. So now put the values of VAB and VBC. We have already got the values of VAB and VBC. Substitute for VAB as E1 minus IR1. Substitute for VBC as E2 minus IR2. Now we shall slightly rearrange this equation. E1 and E2 we shall put in one bracket. So it will become E1 plus E2 in one bracket. In the second term of both, minus I is common. So I have taken minus I also. What remains here is R1 plus R2. So another bracket is R1 plus R2. This I will call it as equation 1. So I got the effective feeding across the series combination. I got the value of VAC. Now another equation for VAC can be obtained using the second figure. So what is the second circuit? This is called as the equivalent circuit. So what we have done here, same thing. In place of two cells, I have connected only a single cell. For the single cell, the EMF is EEQ and the internal resistance is REQ. So here the current was I flowing under the PD VAC. Here also the same current I flows under the PD VAC. So whatever effect the two cells are producing, the same effect is produced by the single cell. So this single cell is called as the equivalent cell. And for this equivalent cell, our aim is to find out what is the value of equivalent EMF and what is the value of equivalent internal resistance. Now we have got an equation for VAC from the first diagram. We shall get an equation for VAC from the second diagram. You can see here. Let us find out PD across the single cell equivalent cell. Again use the same equation. So this single cell is connected between the points A and C. So I shall write this as VAC for the single cell. So VAC will be equals to EMF, that is EEQ minus I is the same, R is replaced by REQ. So I got another equation for VAC, EEQ minus RREQ. So let me call this as equation 2. So you can observe equations 1 and 2, both are for VAC. Now you can very easily compare the two equations. If you compare the two equations, you can find out, if you compare the first term of both the equations, you will find out EEQ is equal to nothing but E1 plus E2. That I have written here. So EEQ, equivalent EMF, is equals to E1 plus E2. The second term you can also compare, minus I is the same for both. What remains here? REQ is comparable to R1 plus R2. So I have written it here. REQ is equals to R1 plus R2. So these are your final expressions. This is equivalent EMF and this is equivalent internal resistance. You can just put them in words. What is the value of equivalent EMF of two cells in series? So you can put in words like this. Equivalent EMF of two cells in series is equal to sum of individual EMFs. Similarly, equivalent internal resistance of two cells in series is equal to sum of individual internal resistances. And this combination, series combination, you can extend it to n number of cells. Suppose you have n number of cells, this equation goes on continuing E1 plus E2 plus so on, last cell will be En. Similarly, R1 plus R2 so on, last will be nothing but R. So it is not restricted only for two cells, you can extend it to n number of cells. So very easy to remember, just sum, here also it is just the sum. So this is about equivalent EMF and equivalent internal resistance of two cells in series. Now one question is, suppose instead of connecting negative to positive, I will reverse the second cell. Suppose I am connecting this minus plus. So what changes are going to happen? Only I have reversed the second cell. If I reverse the second cell, negative to negative, then I have to change the sign. This becomes minus. E1 minus E2. So if I reverse any cell in the series combination, that EMF will come with a negative sign. That is the only change. Now, what are the main points in the derivations? First one is diagram for two cells, then the equivalent diagram. Then what you have to remember for the series combination is when you connect cells in series, current flowing through each cell remains the same, but the terminal PD across each cell goes on varying. So start for terminal PD across the series combination, you get it from first figure, you will get one equation from the first figure. Then again from the second figure you will get another equation for VAC. Compare the two and you get the final equation. So these are only the steps in the series combination. Now one question is, why you have to connect the cells in series? What happens? Suppose you have taken a single cell which you use in your clocks, wall clocks. That single cell, you know, the EMF will be 1.5 volt. It is a very small voltage. Suppose you want to use it in toys or you want to in torch, then you have to connect a number of cells. So if you connect a number of cells, that becomes a battery. So if you want to connect a number of cells, what is the advantage of connecting cells in series? Suppose 1.5 volt each, suppose I connect two cells, total voltage will be 1.5 into 2, I get 3 volt. So if you want to increase the voltage, here I am telling you. If you are going to increase the number of cells, then the voltage also goes on increasing. So if you want more voltage, more output voltage, then you have to connect the cells in series. And for parallel, I told you, if you want more current in the circuit, you have to connect the cells in parallel. And if you want more voltage in the circuit, you have to connect the cells in series. So this is the advantage. But there in parallel combination, lifetime of the cell increases. But here lifetime of the cell does not increase. That is the disadvantage. So this is about your series combination. So maximum marks for this question will be 3. It is not a lengthy derivation like parallel combination. Parallel combination is asked for 5 marks. This you can expect for 3 marks. Now let us go to the next very important point. At the end of the chapter we have Kirchhoff's laws and Wheatstone's network. So to understand Kirchhoff's laws, you need to know some elementary definitions regarding an electrical network, a junction and a loop. So I will just tell you the basic definitions of this so that you can understand the Kirchhoff's laws very clearly. So let us come to the network first. I am taking one simple example here. You can see this example. One cell is E1 with internal resistance R1 connected to R1. This is another resistance R3. Then another resistance is R2 here connected with the cell P2. You can see the whole circuit like this. So what do you observe in the circuit? This is not a simple circuit which you have used for Ohm's law. So here a number of sources are there, a number of components are there. Need not be always the resistors, you can have inductors, you can have capacitors like that. So if you have a number of electrical sources and if you have a number of circuit elements and if they are connected in a very complex manner, then that complex circuit is called as a network. So network is nothing but a complex circuit. For Ohm's law, we always use a simple circuit, that is you have only one cell, then you have some series and parallel combination of resistors, then very easily you can apply Ohm's law, you can analyze the simple circuit. But when the circuit becomes more complex, then Ohm's law cannot be used to analyze that circuit. So to analyze the complex circuit, one more law is used. Two laws are there given by Kirchhoff. So these are called as Kirchhoff's laws. So Kirchhoff's laws are used to analyze complex circuit. Complex circuit is nothing but network. Network means what? Combination of number of cells and number of circuit components in a complex manner. And to analyze this complex circuit, that is a network, we have to use Kirchhoff's laws. So this is the first definition. A complex circuit is called as a network. Now come to the second important point, very important definition, junction. See the same circuit now. You can observe some points like capital here, junction C and F. So this is one junction and this is another junction. What do you observe at the junction? How many conductors are meeting here? 1, 2 and 3. So more than 2 conductors meet at a point, then that point is called as a junction. If you observe this here, again there are 3 wires are meeting at a point, so this becomes a junction. Don't get confused with this. This is just a turning point. Here 2 wires are there. It is called as a node. Node is different and a junction is different. Sometimes the 2 words are used in the book, but it is a wrong concept. These are the just turning points. Junctions are this. So if more than 2 conductors meet at a point, then that point is called as a junction. So here we have 2 junctions here, C and F. Now the third definition is also very important, a loop. So what is a loop now? This circuit, if you see, how many loops do you observe and what is a loop? You can see this is a big circuit like this. Now here I will take 3 loops. Say I start from the point A. I shall find out the closed path for current. So what is that closed path? I start with A, B, C, F and A. I shall come back to the same point. I have written here A, B, C, F, A. This is one closed path for a current. So this closed path for a current is called as a loop. Now here one more. You can get another loop. You can start with C point, C, D, E, F and again C. Now in the loops you see, the starting point and the end point always will be the same. That is called as a loop. So wherever from which point you start, you end up at the same point. So that becomes a loop or that becomes a closed path. So this is one more closed path. C, D, E, F, C. This is another closed path. So this again becomes a loop. Now these 2 loops are contained in one more big loop, which is that big loop. So you can start with this big loop A, B, C, D, E, F, A. So this again becomes another big loop. So this big loop contains these 2 small loops. So all 3 loops are possible here. So what is a loop? So loop is nothing but a closed path for current. So for junction and loop, 2 Kirchhoff's laws are used. One law is used for the junction. It is called as Kirchhoff's junction rule. Another Kirchhoff's law is used to analyze the loop. That is called as Kirchhoff's loop rule. So 2 laws are applicable, one at the junction, another at the loop. So what are these 3 basic terms? I will tell you in 3 sentences. What do you mean by a network? What do you mean by a junction? And what do you mean by a loop? What is a network? A network is an arrangement or combination of a number of electrical sources, a number of circuit elements like inductors, capacitors, resistors. They are all connected in a very complex manner, and that complex circuit is called as a network. So network is a complex circuit. Now to analyze a network, which law can be used? Simple law, simple Ohm's law cannot be used for this complex circuit. If you want to analyze the complex circuit, you have to use which law? The Kirchhoff's law. Now to understand Kirchhoff's law, 2 terms we have defined. One is a junction, another is a loop. What is a junction? A junction is a point in a network at which more than 2 conductors meet. That point is called as a junction. And what is a loop? Loop is nothing but a closed path for electrical current. So many loops can be possible in a complex circuit, but it should be a closed path. So starting point and the end point remain the same. Such a closed path for current is called as a loop. So remember these 3 definitions, and based on 3 definitions we shall state the 2 important laws given by Kirchhoff. This is all for today's session. Thank you.